energy balancing refers to techniques for calculating energy use and energy waste. Today we'll look at some different ways that the term is used, some examples of energy balancing, and how energy balancing might be applied in different job roles. Kevin, the energy efficiency skill sets refers to energy balancing at various AQF levels. But what does energy balancing actually mean?
The term energy balancing is used in a couple of different ways, and I guess it's important to not get too hung up on the terminology. Sometimes the term is used to refer to the overall picture of where and what type of energy is used in a business, and we can see this in the pie charts on the screen. In this sense, you can see how the energy is balanced around, say, 100% of the pie. Energy balancing is based on the first law of thermodynamics, which says that energy is never created nor destroyed, just changes form. So in our pie chart, we have 100% of our energy accounted for, because we've got a pretty good idea of where the energy is used across the business. So that's all good. But if we look at parts of the business or a particular process, can we account for all of the energy? Usually we can't. And so energy balancing often refers to the techniques for calculating the balance of energy going into and leaving a process. And again, if 100% is accounted for, it's all good. If it doesn't balance, well, where's it gone? Well, typically it's either stored in the system, and we can tell this because the system's getting hotter, or it's lost out of the system. And both of these are waste. Now, we've covered some of these concepts in other videos, looking at energy efficiency, looking at energy trading, and looking at lighting. But we'll look at more detail at how to apply this to identifying waste. In another video, we looked at a kettle in terms of its energy efficiency. We found it was 84% efficient. So we could use this to compare other kettles. So we found that the waste is often in heat. Sometimes we can find ways to capture and use that heat for something productive, and this of course is a type of energy trading. And these are related concepts. But energy balancing allows us to know whether energy is being wasted, and we might then use it to identify where that waste is.
Let's look at some examples of energy balancing, starting with a clip of our guest presenter, Chris Wilson, explaining a simple energy balance with lighting.
A very simple example might be to look at halogen light and think about the nominal light power or lamp power that it's using. So for example, with most halogens it's 50 watts. Then you've got the transformer, which uses a certain amount of power, usually about 12 watts, and then you've got the wiring losses going back to the circuit that it's coming from. They all go towards producing the end product, which is light. So for example, if I had a halogen light using 50 watts and the transformer as well using 12 watts, and then I change that over to an LED lamp which is only using between 8 and 12 watts, and I bypass the transformer completely, then I've already made a big saving there. And what I can do is very simply model that.
So all of the videos that we're showing today are available from the sustainabilityskills.net.au website. And I'm just noticing some people are having some technical issues, so I'll just mention that all of the material from today will be available as video segments again from that website in the future. So if you feel that you're missing bits today, it will be available in the future. Kevin, can you run us through some calculations for another simple energy balance using the kettle example?
Sure. If you saw the other one, you'll know some of this data, but let's just run over it again. The kettle had a rating plate which said it was 2200 watts. It takes 2 minutes and 55 seconds to raise 1 litre of water from 20 degrees C to boiling point, and then took another 7 seconds before it turned off. Now we know that a watt is a joule per second, so in the 3 minutes 2 seconds, which is 182 seconds that the kettle was on, it used 2200 watts times 182 seconds, which gives us 400,400 joules, or 400.4 kilojoules. So that's what was used. But how much was actually used to heat the water? Now, fortuitously, a litre of water has a mass of 1 kilogram. We've heated it from 20 degrees C to the boiling point of 100 degrees C, and we know that the specific heat capacity of water is 4.21 kilojoules per kilogram Kelvin. And you just look this up on the web, or if you're old-fashioned in the textbook, just make sure it's in the same units as the data you're using. If we then multiply all of that together, 1 kilo by 4.21 by 80 degrees gives us 336.8 kilojoules. So this is the theoretical amount of heat needed to heat the water. The heat required to just heat the water and only the water with no waste. But we just calculated we have in fact used 400.4 kilojoules. So what happened to the remaining 63.6 kilojoules? Well, clearly this is a waste, and it's almost 16% of the energy we've used. Now we can go a number of different directions at this point. We could say, well, gee, our kettle's only 84% efficient, we'll go and look for a better one. But maybe we actually want to dig into the waste and the different causes of the waste and find out what our most significant cause of waste is.
Okay, we'll come back to that in a minute. Chris, could you explain, because you also use energy balancing, often looking at more complex processes. Could you give us an example?
Sure, Celeste. And I guess this example is looking at more of an overall process and a specific area of a site. So we're looking at making up a picture of that pie and trying to balance it out. So if we take the example of a manufacturing company that has several large machines and they're all using inductive motors, as well as using compressors, air conditioning, lighting, etc., the proportion that each of these uses can be determined in two ways. The first is to estimate consumption by taking the rated power stated on the nameplate. As I mentioned before, you can usually find these on the on the actual devices themselves. For example, you might say it's 150 watts. Then multiplying this by the amount of use. So, for example, 12 hours a day, 5 days a week, 50 weeks per year. We also need to estimate the load capacity factor, as I mentioned before. So this is a number between 0 and 1. This is the best guess estimate of how loaded a motor is when running. Rarely is a motor loaded to the maximum rated current. That is what's shown on the nameplate. For example, an air compressor is often running at an average of 60% load factor as it cycles from a loaded state, or 100%, to an unloaded state of 30%. Air compressors can in general be easy to estimate as you can hear the changes and measure the time intervals. And say, for example, a complex conveyor line with many numerous motors running at different speeds, or process line with start-stop cycling features. This will give a total annual consumption in kilowatt hours for that machine. Once we do this for each machine or type of equipment, the proportion that they contribute to the total use for that site can be determined. We can also compare this estimate to the billing data and see if it agrees. And if it doesn't, then we've got some waste somewhere that we need to identify. But a more accurate way, which Kevin touched on earlier, is to use data logging with current transformers, or CTs, to log the specific circuit that that machine is using and then extrapolate from that the annual use. Usually logging's done over a 1 to 2 week period, so trying to take into account the cycles of the production series. But even a short time span of 10 to 15 minutes can be enough, provided the working conditions remain reasonably constant over time. The logging will give several outputs. These are generally uniform and relate to the voltage and volts, the current, which is in amps, and the power factor. If the equipment is running on 3 phases, then each phase will have a separate output. Taking the average value over the recorded period for each unit and multiplying will determine the average kilowatt power rating. So these are different techniques which you can use, which you can use and depend on how accurate you would need the results to be. So an example of the differences can arise from these two different types of analysis can be seen in the table shown here. And this is a comparison between the proportional energy used by different types of equipment, and one's been done just based on the nameplate rating. Another was actually done through logging, through data logging. So you can see that the results there are quite different, and it means that the proportional contribution of each component is quite different. And also it shows that the logging data has a much closer alignment to what the actual bills showed. There's 40% difference in the estimates from the nameplating, so that's quite a big difference. The other benefit of this is that it shows us much more accurately where we can focus our energy efficiency initiatives. So for this particular company, those top 4 categories there, or activities, the millings and the main rotors, the breakers and the conveyor line, were all looked at being replaced. And they wanted to get a very good idea about what the current usage was and what the usage would be from a new system. And basically, the new system, based on the nameplates that the manufacturer provided, would actually use pretty much the equivalent amount of energy, but it would do the job and twice as fast, and so increasing the throughput of production, and thereby reducing the time it took to get the same amount out.
Evan, you mentioned that you can also use energy balancing to identify where the waste is. Can you give us some examples of how you might do that?
Well, let's go back and look at our kettle. We worked out there was some waste, but we need to dig in a bit further. We can see that we could have different types of waste. The waste could come from heating up the kettle. I guess we can't avoid this, although different kettles may make this lower. There's waste from heating up the air. This is something we should avoid. We get no benefit back from that. There's a waste from actually boiling the water, which takes a lot of energy, although all we want is liquid water at 100 degrees C. We're not actually after the steam. Also, I boiled a litre of water. Now, if I was only making 1 cup of coffee, I probably only needed 250 mil. So that's a further possible source of waste. We can do some energy balancing calculations around here to work out which is the most significant waste we need to follow through on. So just to keep this a bit simple so we don't use up too much time or have too many eyes glazing over, let's assume I did want to boil 1 litre of water, that I needed that, and no significant amount of steam was raised. So the waste then, due to boiling for 7 seconds too long, remember it took 7 seconds after it reached boiling before it turned off, is just a simple proportion, 7 divided by the total of 182 seconds it was turned on for. So 7 to 180 seconds, or 400.4, is 15.4 kilojoules. And of course we heated up the kettle, can't avoid that. So the kettle weighs 423 grams, it's made of polypropylene. So again, we look up the specific heat capacity of polypropylene and find it 0.46 kilojoules per kilogram Kelvin. Same equation as we used before, mass times specific heat capacity times temperature difference, so that's 0.423 times 0.46 times 80, gives us a waste heat in heating the kettle of 15.6 kilojoules. I could, I suppose, actually calculate the heat loss to the air. But this is way too complex for me to do because it changes as the kettle gets hotter. So it's a lot easier just to use an energy balance. I know my total waste heat was 63.6 kilojoules. I know the waste heat from boiling for too long was 15.4. From heating up the kettle was 15.6. So if I take both of those away from the 63.6 total waste, I end up with 32.6 kilojoules of waste, most of which would have gone into the air. And so this is actually quite useful because it tells us that the most significant waste, in fact, is the heat rejected to the air. So buying a new kettle may not improve my overall efficiency all that much. Insulating the kettle will be a much more effective way of increasing its efficiency.
Kevin, across the range of simple to more complex energy balancing, who in a business might need to do these different calculations?
Well, I guess an energy balance can be done by anyone with the numeracy skill to handle the maths. At the bottom level, this is just multiplication and addition. More complex situations, you've got to get into simultaneous equations or with the use of matrices or however you do that, or other more complex maths. So the complexity depends on the amount of data available and the number of unknowns which you need to handle. This might be of most interest to the RTOs present, but because energy balancing comes up at several AQF levels in the energy efficiency skill set and the sustainable operations qualifications. But these levels of complexity also relate to job roles, and so I'll just take a minute to look at these. If we look at the unit MSS 014006A, contribute to sustainability related audits, this requires energy balancing within a work area or process. So it uses the same techniques that we've just looked at with the kettle. It's got a relatively small scope because it's applied to a defined work area, and therefore the maths should be relatively simple. And so we might expect this to be done by a team leader or a supervisor with appropriate level of numeracy. And so typically this would be at this level basic algebra, only one or two unknowns, and most of the data will either be sourced using meters or data logging or looked up simply on the web. If we move up to the diploma units, MSS 015011A, conduct a sustainability energy audit. This requires calculation of energy balances for a process site or value chain. So this is over a much larger part of the value chain, and this therefore increases the complexity quite a bit, although still not as complex as the graduate diploma unit. MSS 015002A develops strategies for more sustainable use of resources, also requires methods of energy balancing to be used as a tool. So here we might be expecting a technician or a numerate manager to be undertaking these. We'd expect them to be able to handle equations with a moderate number of variables, 2, perhaps 3 unknowns. Maybe we need a couple of pre-calculations in order to calculate the values we're going to put into our energy balancing. Finally, getting along to the graduate diploma unit, MSS 017002A, determine process loss through mass or energy balancing. This unit, if we dig into it, requires the use of tables of thermodynamic properties, and as that's a bit of a mouthful, we normally just call them steam tables. Also requires the use of specific heat capacity, specific latent heat, combined mass energy balancing, including the use of heats of reaction, dissolution, and so at this level, it's actually quite complex. So typically you'd expect this to be done by an engineer, a chemist, or other technical specialist. This complexity is much greater than the others. And so typically, if you're doing a combined mass energy balance, say you're cooking biscuits, the mass of biscuit going into the oven is greater than the mass of biscuit coming out. So you'd need to look up your steam tables to work out, first do a mass balance to work out how much water was lost, then look up your steam tables to work out how much energy that is, and then you do the rest of the energy balance.
Energy balancing can be used to identify where energy is being used across a business and to identify where it's being wasted. We've explained a couple of ways that this can be done and how it might be used in a business. And we've worked through some simple calculations and outlined how the calculations become more complex when you apply energy balancing across a more complex process.